Welcome to Lecture 22, in which we will now revisit Example 4 from Lecture 20. You will recall that in Lecture 21, we also considered Example 4, and we, in that case, looked at an approach based on, let me actually back up. Recall that Example 4 here ask us to find a unitary transformation that would have this action on the 0, 0 ket. And really that was all that we required, was that the transformation act on the 0, 0 ket in this way. We did not care how it acted on the 0, 1 ket or the 1, 0 ket or the 1, 1 ket. However, the approach that we discussed in Lecture 21 was based on going ahead and making assumptions about how the transformation would act on the other kets, and then from those assumptions we were able to obtain a matrix for what was essentially a general unitary transformation. And then in Lecture 21, we discussed how to implement a general unitary transformation. In other words, we showed how to write a general unitary transformation as a product of two-level unitary transformations, because once we do that, then we know easily how to implement each one of those two-level unitary transformations. So that was the approach we took in Lecture 21. But as was noted at the time, that was somewhat tedious. And so let's, in this lecture, we're going to revisit the problem. And instead of making assumptions about how the transformation U4, which actually I'm probably going to be calling U most of the time, but instead of making assumptions about how U acts on the other kets, we'll just stick with this one assumption and make no assumptions about how it acts on the others. So in fact, I am going to go ahead and change the title or change the name of this to U instead of U4, but keep in mind that it's the same transformation that was being discussed in Example 4 from Lecture 20. That's the only reason it had that subscript of 4, is because it was in Example 4. Okay, so we want a unitary transformation that has this effect on the 0, 0 ket, and we're not going to make any assumptions on how it affects other kets, because as we saw in Lecture 21, that can lead to a rather tedious problem. So we're going to try to see if we can find a simpler approach than the approach that was discussed in Lecture 21. Now, for the lectures that I'm about to present, for the approaches that I'm about to present, all of these approaches will begin with the idea that was presented to you in problem 20.3. That was the last problem on test 20. And so let's review that problem. And it's shown right here. It says, suppose that we have the following. We have U1 is a two-level unitary transformation that acts on 0, 0 and yields A0, 0 plus B0, 1. U2 is a two-level unitary transformation that also acts on 0, 0, but it yields C0, 0 plus D1, 0. And U3 is a two-level unitary transformation that acts on 0, 0 and gives E0, 0 plus F1, 1. Actually, I've gotten a little bit ahead of myself. These statements here do not imply necessarily that these unitary transformations are two-level, but that's given in the following information. So here's the action of U1, U2, and U3 on the 0, 0 ket. And then, as is said here, if it is also given that U1 and U2 and U3 are two-level unitary transformations, and that none of the numbers A, B, C, D, E, or F has a magnitude of either 0 or 1, then we ask, what is U3 of U2 of U1 of 0, 0. And you're given 4 choices here. And unfortunately in the test, well, the correct answer is B, as we will now find, but the B was written incorrectly on your test, so this will give me a chance to correct that error as well. So how do we arrive at this answer B? And the first approach that I want to talk about here is a very simple approach that goes as follows. Okay, we want U3, U2, U1 of 0, 0. And by the way, just to make sure that you understand what this notation means, that means U3 of U2 of U1 of 0, 0. Okay? So now, let's, well, before we actually compute this, let me make a note for you. Let's come back up here and look at the given information. Since U2, well, let's start with U1. U1 is 2 level, and we're told here that U1 of the 0, 0 cat is A0, 0 plus B0, 1, where B is not equal to 0. So that means right away that 0, 0 is, you know, since U1 is 2 level, it affects only 2 states in a non-trivial way, and since B is not equal to 0, that tells us that one of the states that is non-trivially affected by U1 is the 0, 0, and also that the other one is 0, 1. So we know immediately that U1 will act trivially on 1, 0 and 1, 1. So we can say U0 of 1, 0 is equal to 1, 0, and U1 of 1, 1 is 1, 1. And again, the reason that we can say that is that from this equation and from the fact that U1 is 2 level, we can immediately say that the only 2 states that U1 affects in a non-trivial way are the 0, 0 state and the 0, 1 state, and therefore U1 of 1, 0 is 1, 0, U1 of 1, 1 is 1, 1. That is, U1 acts trivially on those 2 states. And in a similar fashion, we can conclude that U2 acts non-trivially only on 0, 0 and 1, 0, so that means U2 of 0, 1 is equal to 0, 1, and U2 of 1, 1 is equal to 1, 1, and finally U3 acts non-trivially only on 0, 0 and 1, 1, so U3 of 0, 1 is equal to 0, 1, and U3 of 1, 0 is equal to 1, 0. And these pieces of information will be useful to us in the solution procedure that we will outline here. So let's see how this goes. Well, inside here we have U1 of 0, 0. And we're given above that U1 of 0, 0 is A0, 0 plus B0, 1. So we can write that down. A0, 0 plus B0, 1. And now we use the fact that U2 is linear to say that U2 of this superposition is equal to A times U2 of 0, 0 plus B times U2 of 0, 1. Now, U2 of 0, 0 is given above, and it is equal to C0, 0 plus D1, 0. So for U2 of 0, 0, we put C0, 0 plus D1, 0. Now, what about this other term, B times U2 of 0, 1? Well, if we look up, here, U2 of 0, 1 is just 0, 1. So here we can write 0, 1. And now when we multiply out what's inside the parentheses, we get AC 0, 0 plus AD 1, 0 plus B 0, 1. And now, just like U2 is linear, so is U3, and so U3 acting on this superposition is equal to the following. We have AC times U3 of 0, 0 plus AD times U3 of 1, 0 plus B times U3 of 0, 1. And so now we look above, U3 of 0, 0 is given to be E0, 0 plus F1, 1. U3 of 1, 0 is given over here to be 1, 0, and likewise we'll use next U3 of 0, 1 is 0, 1, and so this becomes 1, 0, and then the last term becomes B 0, 1, and therefore our final answer is that U3, U2, U1 acting on 0, 0 is equal to ACE 0, 0 plus ACF 1, 1 plus AD 1, 0 plus B 0, 1. And if you check, you will see that that matches the answer B, which has now been modified. Once again, on your test, some of these coefficients were incorrect, but now this is the correct answer. So this would be one way of solving problem 20.3. And if we solve the problem in that way, and now we're looking for approach, so we'll say, how does this help us to solve example 4, well, it's obvious how it helps us to solve example 4, because remember, as we stated above, in example 4 we have u, and again I've dropped the subscript of 4 here, we have u find u such that, well, not just find, but we wanted to implement u such that u of 0, 0 is equal to square root of 1/10 0, 0 plus square root of 2/10 0, 1 plus square root of 3/10 1, 0 plus square root of 4/10 1, 1. As you can see up here. Oh wait, I'm sorry, I have 1, 1 and 1, 0 reversed, so let's correct that down here. This should be 1, 1, and the last one is 1, 0. Well, now this approach leads to a very simple solution to the problem, because if we compare these two expressions, we see that what we want is ACE. We'll say so ACE is equal to square root of 1/10 ACF is equal to the square root of 3/10 AD is equal to the square root of 4/10, and finally B is equal to the square root of 2/10. And not only that, but we know more than that, because look up here, from the information that's given here, since u1 of 0, 0 is a 0, 0 plus b 0, 1, and this is a unitary transformation, we can say also that the magnitude of a squared plus the magnitude of b squared is equal to 1. The magnitude of c squared plus the magnitude of d squared is equal to 1. And the magnitude of e squared plus the magnitude of f squared is equal to 1. So coming back down here, we have identified that b is equal to the square root of 2/10, and therefore we can say, okay, b equals square root of 2/10 implies that magnitude of b squared is 2/10, which implies that magnitude of a squared is equal to 8/10. So let's try a equals square root of 8/10. In other words, let's see if we can just make this assumption that it's the square root of 8/10 and not worry about there are other possibilities here. We could have some phase term involved that is not equal to 1, but let's just assume, let's give this a try to keep it as simple as possible. So we'll try a equals square root of 8/10. And in fact, in all of these coefficients, we'll hope, we're going to try for positive real coefficients, and I think that we'll find out that this will work. So we're going to try a equals square root of 8/10. Now, if this is true, then we can go then to the equation remember we have here AD equals square root of 4/10. So when we substitute in for A, okay, let's just do it like this. AD equals square root of 4/10. And so with the value of A that we're trying, that would imply that square root of 8/10 times D is equal to the square root of 4/10. And that would imply that D is the square root of 1/2. Again, we're assuming here we're just going to, well, actually this is correct. There's no assumption involved with D if our assumption for A is true. So now we have A is square root of 8/10, D is square root of 1/2, and so now let's notice then that would imply, okay, D equals square root of 1/2. Let's see here. Okay, D equals square root of 1/2 would imply that magnitude of D squared is equal to 1/2, which would imply remember that we have magnitude of C squared plus magnitude of D squared is 1, so this would give us that the magnitude of C squared is 1/2. And so let's try C equals square root of 1/2. And now if C is the square root of 1/2, then we have ACF equals square root of 3/10, would then imply, using our value for A and our value for B, or for C, we'd have square root of 8/10 times the square root of 1/2 times F is equal to square root of 3/10, and that would imply that F is equal to, let's see here, we have, I believe, square root of 3/4. Yes. And then finally, magnitude of E squared, well, let's just say it like this. If F is the square root of 3/4, we could say F equals square root of 3/4 implies a magnitude of F squared is equal to 3/4, and that would imply that magnitude of E squared is 1/4, which implies that well, let's try E equals square root of 1/4. So now let's see if everything here with these assumptions, well, we've made a few assumptions, but let's see if all of this works out. So if we go back now, these are the four equations that must be satisfied are ACE. There are the four equations right here. ACE equals square root of 1/10, ACF equals square root of 3/10, AD equals square root of 4/10, and B equals square root of 2/10. And so let's see if these choices are consistent with that. So A times C times E, we'd have square root of 8/10 times the square root of 1/2, so that'd be square root of 4/10, and then times E would give us square root of 4/10 times the square root of 1/4 would be the square root of 1/10. And ACE is indeed square root of 1/10. So we do check with the first equation. Now what about ACF? Well, square root of 8/10 times the square root of 1/2 is the square root of 4/10, and then the square root of 4/10 times the square root of 3/4 will be the square root of 3/10, and that checks. So ACF is square root of 3/10. Now, what about AD equals square root of 4/10? Well, A is square root of 8/10, D is square root of 1/2, and so when we multiply these together, we do indeed get square root of 4/10, so that checks. And of course, B equals square root of 2/10 is what we've been using to derive the others. And so now we have A, B, C, D, E, and F, which altogether will satisfy all of the equations. And so we're done. We just say now, so the answer is U equals U3, U2, U1, where U3, well, let's do it in the order of U1, U2, and U3. U1 was 0, 0. U2 of 0, 0. U3 of 0, 0. Okay. U1 of 0, 0, remember, is A 0, 0 plus B 0, 1. So since A is square root of 8/10, we'll have square root of 8/10 0, 0 plus B is square root of 2/10 0, 1. U2 of 0, 0 is C 0, 0 plus D 1, 0. C is square root of 1/2. D is also square root of 1/2. So we have square root of 1/2 0, 0 plus square root of 1/2 1, 0. And then finally, for U3, it goes to E 0, 0 plus F 1, 1. And E is square root of 1/4. So we have square root of 1/4 0, 0 plus square root of 3/4 1, 1. And so now we've written U. Now this is a U that will work. It doesn't mean it's the only U that will work, because we could have, as was mentioned, we could have found other values up here. For instance, as I said here, there are really, if we put a phase factor here, there's really an infinite number of A's that would have worked to give us magnitude of A squared equals 8/10. And depending, if we had chosen different A's, then we could have gotten different values for D and so on. So this assumption is one assumption that leads us to one conclusion, but this is not the only possible solution to this problem. But we're not asking for all solutions, we're just asking for a solution, and we have now obtained one. We have written our transformation U as a product of two-level unitary transformations, and we know based on the work we've done up here that you will take the 0, 0 vector to this vector. Where it will take any other vector, we don't know, and really we don't care, because that wasn't part of the problem. We just wanted to find a unitary transformation that would have this effect on the 0, 0 state, and this one that we have found down here will have that effect. And notice that since it is a product of two-level unitary transformations, we could easily find this circuit. So that's the first approach. Now the second approach is one that many students used in trying to solve problem 20.3, and I want to talk about it a little bit as well. So we had, recall, we have this information up here about U1, U2, and U3. And also, as I said, the fact that U1, U2, and U3 are two-level unitary transformations. So many students did the following. Since, for instance, let's look at U1 first. U1 of 0, 0 is A, 0, 0 plus B, 0, 1. And so many students did the following. They said U1, the matrix for U1 was equal to A, B, 0, 0. We know that from the given information. And then, since it's two-level, they know something about the second column as well. And what many people would assume, many people assume something like B minus A, 0, 0, and then 0, 0, 1, 0, and 0, 0, 0, 1. And likewise for U2, from the information given, many people wrote something like this. They said, okay, U2 of 0, 0 is C, 0, 0 plus D, 1, 0. And now we have to figure out what ordering of the basis we have, and let's stick with the same ordering that is given here: square root of 1/10, 0, 0, and then 0, 1, 1, 1, and 1, 0. Let's use that ordering. So if we use that ordering, then U2, we have C and D. So U2 would look as follows. We would have C, 0, D, 0, 0, 1, 0, 0, and then many people put D, 0, minus C, 0, 0, 0, 0, 1. And then finally, for U3, since it's equal to E, 0, 0 plus F, oops, wait, made an error there. If we use the basis ordering that's given here with 1, 0 as the last, see 1, 0 here is the last vector in the basis. And so therefore, if we use that ordering, then our matrix for U2 would not be as shown, but instead would be this. We'd have C, 0, and then D, and then 1, 0, and then D, and minus C. Okay. And then finally, for U3, it's equal to E00. It's sending 00 to E00 plus F11 is shown here. So we would get E0 F0 0 1 0 0, and then again what many people put was F0 minus E0 0 0 0 1. So again, this is an approach that many students used, and there's nothing particularly wrong with it, except that, well, one objection I would have is that, for instance, the fact that U1 of 0, 0 is equal to A00 plus B01, that does indeed give you the AB00 for this first column. But the second column here does not have to be B minus A. It could be minus B positive A. So there would be really two choices for the U1 matrix, two choices likewise for the U2 matrix, because while the first column is definitely C00D, the last column could be D00C or minus D00 positive C. And finally, there's two choices for this one as well. This third column could be minus F 0 positive E 0. So there's really two choices for U3, two for U2, two for U1. And so if we multiply those all together, there would be 8 different possibilities that we would need to check. And now I will admit that if you're clever, you can check all 8 of those really simultaneously by just using plus or minus or plus signs for the appropriate terms. But all of that seems to me to be somewhat akin to what we did in Lecture 21. What I mean is that you're assuming more than needs to be assumed. So let me give you a slight variation on this approach and show you how it works. So I'll say instead, let's go with this, okay? We know that U1, since it maps 0, 0 to A00 plus B01, as I said a moment ago, we know then that the first column is AB00. And secondly, for the second column, we know that the last two terms are 0, but for the first two terms, let's just put question marks. Now, those question marks in all of what I'm about to do, don't interpret the question marks as all representing the same number. A question mark is just something that's unknown. Now, the next two columns of U1 are known, and so we'll put those. Now, likewise, for U2, we definitely know that the first column is C00D, and since U2 acts trivially on 0, 1, the second column must be 0, 1, 0, 0, and since U2 acts trivially on 1, 1, the third column must be 0, 0, 1, 0. But for the fourth column, we're not sure of how U2 acts on 1, 0, and so we just know we know we have a 0 in these two places, but in the top and bottom entries in that column we don't know, so we'll put question marks. And then finally, for U3, following in the same spirit, we'll get E0, F0, and then 0, 1, 0, 0, F, question mark, 0, question mark, 0, 0, 0, 0, 1. Now, again, recall, just to refresh your memory, what we're looking for here is U3 is here, U3, U2, U1 of 0, 0. So now that we have these matrices for U1, U2, and U3, we can calculate this. U3, U2, U1 will be equal to E0 question mark 0, 0, 1, 0, 0, F0 question mark 0, 0, 0, 0, 1, C 0, 0 question mark 0, 1, 0, 0, 0, 0, 1, 0, D 0, 0 question mark, and finally A question mark 0, 0, B question mark 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And let's see what this gives us. We'll bring down the first term, E0 question mark 0, 0, 1, 0, 0, F0 question mark 0, 0, 0, 0, 1. And now we'll multiply out these other two. Now when we multiply C0, 0 question mark times this first column, we'll definitely get AC. C0, 0 question mark, when we multiply it by the second column, C is getting multiplied by a question mark, so we don't know what we'll get for that entry. C0, 0 question mark times this column is definitely going to be 0, because we get 0 times C, which must be 0, 0 times 0, which must be 0, 1 times 0, plus, which must be 0, and 0 times question mark, which must be 0. So we'll get 0 here, and then finally this row times the last column, well, we're going to get a question mark times this 1, and so that gives us a question mark. Now, for 0, 1, 0, 0, when you multiply something like this times a matrix, it's just going to choose the second row. So we get B question mark 0, 0. Likewise, when we multiply this times this matrix, we'll get the third row of the matrix. So 0, 0, 1, 0. And finally, now we're multiplying this row times this matrix. Okay, we're going to get, we don't have to worry about this question mark because it gets multiplied by the 0, so that doesn't, it has to be 0. So we have AD here, and then D0, 0 question mark times this column. Well, the D is getting multiplied by a question mark, so that gives us question mark. D0, 0 question mark times this column will give us 0. And finally, D0, 0 question mark times 0, 0, 0, 1. The question mark is getting multiplied by 1, so we get a question mark. And now to finish this up, we get E0 question mark 0 times this. And notice that the question mark is going to be multiplied by the 0, so there's no problem. We get ACE. When we multiply this row times the second column, E is getting multiplied by the question mark, so we have a question mark there. When we multiply this row times the third column, the question mark here is getting multiplied by 1, so we get a question mark. And this row times the last column, E is getting multiplied by this question mark, so we get a question mark. Now this will just pick out the second row, so we get B question mark 0, 0. This row now times this column, we get the question mark is getting multiplied by 0, so that's okay, and we get ACF. this times the second column, well, F is getting multiplied by question mark, so that gives us a question mark. This multiplied by the third column, this question mark here is getting multiplied by 1, so we get a question mark. And finally, this row times this column, well, F is getting multiplied by question mark, so we get question mark. And then finally, when we multiply this row times this matrix, it'll just pick out the fourth row, so we get AD, question mark, 0, question mark. Now, you might despair because we have all these question marks here in this matrix, but remember, all that we wanted to have was that we wanted to know how U3, U2, U1 acted on the 0, 0 vector, and that's all that information is in the first column. So it's equal to ACE 0, 0 plus B 0, 1 plus ACF 1, 1 plus AD 1, 0. And if you compare, that is exactly the same solution that we reached right here with approach 1. And of course, once again, we could, now that we have this information, we could solve for the coefficients and find our implementation in terms of, well, actually, sorry there. Here, we already have our two-level unitary matrices, and so this is what this is doing is here is our and this is telling us that this implementation right here, as long as we choose these coefficients so that it gives the desired values, then this implementation will work. So that would be a second approach for solving the last problem in test 20, and then also for applying it to example 4. And now, finally, I'd like to discuss a third approach. And it is, again, related to that last problem from test 20, that this is a third approach for finding that U. Let me remind you one more time what we want. That's what we want. We want to find a U that will act on the 0, 0 ket in that way. And this third approach is the one, I'm just putting it in because I think it's sort of an interesting approach. It is the one that I feel gives the most insight into this, but it's also potentially the one that is the most confusing. And so if you don't follow it, fine, no problem. But for some of you might like this, and so we'll see how it goes. Okay, so this third approach will go as follows. We'll say we'll go ahead and have, so we'll suppose we have U1, U2, and U3 as described in problem 20.3. Now, however, we will allow to combine these operators in any order. The order will determine the coefficients. I know that's a little vague right now, but you'll see what I mean. Now, simply so that we'll come up with answers that we can compare to what we had before, I'll use the same order, but from the way that I developed this, I think you'll see that we could do this in any order. Okay. So let's suppose that we apply U1 first. Suppose we apply U1 to 0, 0 first. In fact, I'm going to go ahead and say, actually, let me reword that. Okay, so this means we're going to apply U1 first and then U2 and U3. Now, don't misunderstand. Approach 1 could have had the operators in different order as well. Approach 2 could be done in different order. But I think that this one, well, this is just a different approach, and maybe you'll like it. Maybe some will like it, and probably some won't, but we'll see how it goes. So we're going to apply U1 first. Okay, U1 of 0, 0. Now, the way that we'll look at this is the following. Remember that U1 of 0, 0 is equal to A0, 0 plus B 0, 1. Now, what I'm interested in is that 0, 1 part. I'm not interested in the 0, 0 part right now. I'm interested in the 0, 1 part. And why am I interested in that? Well, that 0, 1 that comes out of U1, we know that U2 will not affect it. U2 of 0, 1 is 0, 1. Likewise, U3 of 0, 1 is 0, 1. So this end result, this square root of 2/10, 0, 1, must have arisen here at this very first step. So this tells us that the 0, 1 part of U1 must be square root of 2/10 times 0, 1. And of course, if that's true, that U1 of that the 0, 1 part of U1 of 0, 0 is square root of 2/10, well, the only other part is the 0, 0 part, and for this to be unitary, it must be then square root of 8/10. 0, 0. So we have U1 just that easily from this argument. Okay, now let's look at U2. Now here you have to be careful. U2 is going to act second. Now, and so again, U1 of 0, 0 is going to give us this, and then U2 is going to act on that. So we have U2 of the square root of 2/10, 1, 0 plus square root of 8/10, 0, 0. Well, this is going to be the square root of 2/10 times u2 of 1, 0 plus the square root of 8/10 times u2 of 0, 0. Sorry. Now, as has already been noted, u2 acts trivially on 1, 0. I guess I should have a parentheses here. u2 acts trivially on 1, 0. And therefore, u2 of 1, 0 is just 1, 0. So we get square root of 2/10 times 1, 0 here. And then out of the rest of this, out of the rest of this here, remember u2 of 0, 0, well, it's going to give us something times 0, 0. I'll just put this as a question mark times 0, 0. Actually, let's do it like this. So I'll say, let's maybe do it like this. Okay, we have square root of 8/10 and u2 of 0, 0, we're told is equal to b 0, 0. Nope, c 0, 0. c 0, 0 plus d 1, 0, I believe. Let's check that. Let's check this problem because we want to make sure this is right. Yes, you see up here, u2 is equal to c of 0, 0 plus d 1, 0. And if I now go one more step, I'll get square root of 2/10 1, 0 plus square root of 8/10 c 0, 0 plus square root of 8/10 d times 1, 0. Now our reasoning is just as it was before. This 1, 0 component here that we get is going to pass right through u3. In other words, u3 acts trivially on 1, 0. It won't affect it at all. And so what we'll get out is square root of 8/10 d times 1, 0. But what we want is square root of 4/10 1, 0. So we know immediately then, we can say, so square root of 8/10 d, again, that's the 1, 0 part, and we know that it will not be modified at the next step because u3 acts trivially on 1, 0. So we have square root of 8/10 d is equal to this end result, which will be square root of 4/10 1, 0. So we get square root of 4/10, and therefore d is equal to square root of 1/2. And of course, if d is square root of 1/2, then we can say, or we can pick, or we'll try, we'll put it that way since that's the way we worded it before. So remember, that magnitude of c squared plus the magnitude of d squared is 1, so we'll try c equals square root of 1/2 as well. And now finally, for the last step, u3 is going to act on what comes out of u2. So we have u3 of square root of 2/10 1 0 plus now square root of 8/10 times c. C is square root of 1/2. So square root of 1/2 times the square root of 8/10 is square root of 4/10. So we get square root of 4/10 0 0. And then similarly here, square root of 8/10 times square root of 1/2 is square root of 4/10. 1 0. Well, what will that be? That will be square root of 2/10 times u3 of 1 0 plus square root of 4/10 u3 of 0 0 plus square root of 4/10 u3 of 1 0. Now, u3 acts trivially on 1 0, so the first term just becomes square root of 2/10 times 1 0. And likewise, for the last term, u3 acts trivially on wait, there's some mistake here. Let's see. u2 of 0 0 is c 0 0. Let's see here. I'm sorry, here's the mistake right here. So in going, okay, this is u1 of 0 0 is this, and then u2, see we have u1 of 0 0, u1 acts on 0 0 first, then u2 acts on the result of that, and then u3 acts on the result of that. Well, u1 of 0 0 we found was equal to this here, right here, square root of 2/10 0 1 plus square root of 8/10 0 0. But when I transferred that down to here to let u2 act, I transposed the 0 1 and 1 0. So let's get that straight. This should be 0 1, and likewise then this will become 0 1, and u2 acts trivially on 0 1, and therefore this is 0 1, and of course we'll bring that down here. Now all of our argument over here stays exactly the same. That was just a switching of the two, or transcription you might say, of the two numbers there. So okay, so we have 0 1 down here, but all of the argument over here is still the same. u2 of 0 0 is c 0 0 plus d 1 0, and then when we multiply that out by the square root of 8/10, we get this. And again, our reasoning then is that the only other operation that's going to act on this is u3, and we know that u3 does not change the 0 1, it does not change 1 0, so those two are going to slip through. Now we've already fixed this coefficient so that we're going to end up with the right thing in the end, but now we need to fix this coefficient so that we come out with the right coefficient here for 1 0. And so we do that by saying square root of 8/10 times d is equal to square root of 4/10, which gives us d is square root of 1/2. And so we'll try to go with that C equals square root of 1/2. And now when we stick that in here, okay, again, correcting this transcription, we have 0, 1 there, and likewise then that will become 0, 1 here, and finally then U3 of 0, 1 is indeed 0, 1. So now we have that taken care of, and now to continue to finish our argument. Okay, not only does U3 act trivially on 0, 1, but U3 also acts trivially on this last term, 1, 0, so we get square root of 4 over 10, 1, 0, and then finally we get square root of 4, well, it's, yes, 4/10, and U3 of 0, 0, we're told is E 0, 0 plus F 1, 1, and therefore when we put this all together we get U3, U2, U1 of 0, 0 is equal to square root of 2/10, 0, 1 plus square root of 4/10, 1, 0 plus square root of 4/10 E 0, 0 plus square root of 4/10 F 1, 1. And if we compare that to our goal, we see that the 1, 0 let's see, the 0, 0 coefficient right now is the square root of 4/10 E. The final coefficient for 0, 0 is desired to be square root of 1/10. So we get the equation square root of 4/10 E equals square root of 1/10. And for the coefficient of 1, 1, we look up here. The coefficient of 1, 1 is desired to be square root of square root of 3/10. And so we get square root of 4/10 F is equal to square root of 3/10. The other two coefficients here are already determined. And so, of course, we get E equals square root of 1/4, and F equals square root of 3/4. And if you compare our values for E and F and C and D, and of course, here, square root of 2/10 is A. Excuse me. Notice we've written these two states in reverse of the usual order. So this would be B, and this would be A. And if you compare the values we've obtained now with this approach, A equals square root of 8/10, B equals square root of 2/10, C and D are both equal to square root of 1/2, and E is square root of 1/4, F is square root of 3/4. If you compare that to what we obtained up here, you will see that it is exactly the same. And so this last approach is still another that you might use. And as I say, I think it's sort of an interesting approach simply because it gives a little more insight into what's going on and how some vectors are passing through these operations. And one more comment before we get to the problems. You might ask yourself in this second approach, why do we have zeros? Why, despite the fact that we have so many question marks up here, why can we still say that U3 times U2 times U1 will have 0 in these three locations? That would be an interesting thing to think about. What it's saying is that U3 times U2 times U1, well, I'll leave it to you to decide what how do we know that these are zeros? And I'm talking about not from the multiplication point of view, that we see easily, but what I'm saying is, physically speaking, when we consider how these different operators work, how is it that we know that these terms will be zero? If you can think about that, I think it would be useful. So anyway, that finishes up. We've certainly talked about this in detail, and so now let's look at some problems. Okay, for all of the problems, we'll have all the problems will refer to the following situation. Suppose for some reason my pen is not working here. Let me break for a moment. Now, okay, sorry about that. And now the eraser is not working. So indeed, let me break for just a moment. I don't know what was recording, but okay, it seems that I'm recording now. Okay, so anyway, all of the problems will refer to the following situation. We'll say, suppose U1, U2, and U3 are as given in problem 20.3 above, and we want U to be as given above. In other words, U acting on 0, 0 is equal to the square root of 1/10 0, 0 plus square root of 2/10 0, 1 plus square root of 3/10 1, 1 plus square root of 4/10 1, 0. Okay? So now the question is this: if we want to implement U as U equals U2, U3, U1, so now this is, actually, let me change that. Let's say U1, U3, U2. Now keep in mind, above we have U3, as you can see here, and in other places we have U3, U2, U1. That's the expression for U. But now we're going to have U is equal to U1, U3, U2. And I'll say, if we want to implement U as U equals U1, U3, U2, find positive, real positive values for A, B, C, D, E, and F that will work. And when we restrict these to all being real and positive, there are unique answers. And so we'll say this is lecture 22, so 22.1 A, 22.2 B, 22.3 is C, 22.4 will be D, 22.5 will be E, and 22.6 will be F. So these are not multiple choice questions. These are just asking you to find the values for A, B, C, D, E, and F. And again, now, as you know, you can take any one of the approaches that we have above, but just make sure that the values turn out. I know that there will be, these values are not unique unless you add extra requirements, and the extra requirement that I'm imposing is that all of them must be real and positive. And once you require that, then the values will be unique. And so you should find A, B, C, D, E, and F that will give us a U that will behave in this way, and also that can be written as U1 times U3, or U1 of U3 of U2, where U1, U2, and U3 are as shown right here in this problem. U1, U2, and U3 are all two-level unitary transformations, and U1 is A00 plus B01, U2 of 00 is C00 plus D10, and U3 of 00 is E00 plus F11. You need to find A, B, C, D, E, and F in this equation. And so that is it. I'm afraid, once again, this lecture has taken a bit longer than expected, but I promise to try to make that up to you very soon. So that's it, and good luck.